back to the video series on semiconductor devices. Through our previous videos, we were trying to understand the physics of semiconductors. We had gone through many theories and have understood what mobility is, what are the carriers inside the semiconductors, how they react to the electric field, what is a diffusion, so on and so forth. In today's video, we will be trying to assimilate these concepts into mathematical equations. So we will see few relations that will help you to understand more about the working of devices using semiconductors. The first of our topic will be Einstein Relation. Don't be surprised to know that Einstein has also contributed in semiconductor physics. In order to understand this relation, we will consider few assumptions. We take that there are no net current flowing in a semiconductor material. In other words, at equilibrium condition, the drift current will be equal to diffusion current, will be equal and opposite to diffusion current, so that the net current will be zero. How this is happening, we will discuss in detail. As we had already mentioned, for any explanation, we will be considering one type of semiconductor and do the math, and then we will map it to the other type of semiconductor. Here we will be taking the n-type semiconductor to explain these relations, which means we are dealing with one kind of carrier. N-type semiconductor, the majority carriers are electrons. And no external field is applied. This is another point that you have to keep in mind. No external field is applied. Then the question will be, how can there be a drift current if there is no external field? You have to understand the fact that drift current is the current due to the field applied, which need not be external electric field. Even there will be an electric field due to change in concentration of the doping. So here the drift current is produced by the electric field, which is due to the change in concentration of doping. So this is the premise that you have to keep in mind. We are taking an n-type semiconductor so that the carrier that we are dealing will be electrons. There is no external electric field applied, but there is a drift current due to the field which is brought about by the concentration, change in the concentration of doping. And at equilibrium, we take it as the drift current will be opposite and equal to the diffusion current in the semiconductor. In order to understand this concept, we will look into an energy band diagram. This is different from the normal energy band diagram that we had seen earlier, because the conduction band and valence band are having a slope. It is not parallel to the Fermi level. This slope is due to the change in the doping concentration if we consider the picture from left to right. And this slope is creating an electric field which introduces the drift current. And as you see in the figure, EF, the Fermi level, is not having slope because we are considering the equilibrium condition. And Since there is an electric field, there will be a drift current. And at equilibrium, we have to consider another factor of the current, which is the diffusion current. As you all know, the diffusion current is due to the difference in concentration of carriers. The concentration of the carriers is different. That can be understood from the figure itself. At the left side of the energy band, the gap between the conduction band and the Fermi level is small. So at that point, there will be more electrons in the conduction band. As we move from left to right, this gap increases. As the gap increases, the concentration of electrons decreases. So in the conduction band, there is a change in concentration as we move from left to right. This variation in the conduction band, the carriers in the conduction band, will cause the diffusion current. And at equilibrium, the drift current will be equal to the diffusion current, so that the net flow of current in the semiconductor that we have considered, where we don't have any external electric field, so the net current will be 0. Now we will do the math related to this. We already saw the equations for drift current and diffusion current. I am just repeating it here so that you get reminded with these equations so that we can move ahead in our discussion. Drift current is given by Q, which is the charge of the electron, mu, which is the mobility, Nx is the electron concentration, or the number of electrons, and Fx is the field. In case of diffusion current, which is given by Q, again the charge of electron, dN is the coefficient of diffusion, and also dnx by dx, which is the rate of change of electron concentration as we move from one point to another. And as we have posted earlier, at equilibrium, no net current flows, or the sum of the drift current and the diffusion current will be equal to 0. We are equating the drift current and the diffusion current by rearranging. We get Q dnx by dx is equal to minus Q mu nx fx. This equation we have written because at equilibrium no net current flows. Now we will substitute certain values, certain equations in the above equation, the last equation, so that we will get a relation. For that, remember the equation that we had studied earlier, which is the number of electrons n is equal to Nc, which is the effective density of state, e raised to Ef minus Ec divided by kT. When we discussed earlier, I had written e raised to minus of Ec minus Ef by kT. So I have just taken that minus sign inside, so that now we have n is equal to Nc e raised to Ef minus Ec by kT. You know, Ef is the energy of the Fermi level, Ec is the bottom of the conduction band, energy of the bottom of the conduction band, Boltzmann's constant K, and T is the temperature in Kelvin. We make a change in this equation by adding n of x, because we know the number of electrons is dependent on the distance x in the x direction. So n of x is equal to, the only change that happens in the right hand side is in the case of EC, because it is having the slope. EF is not having the slope. Remember the energy band diagram. So only change in the right hand side will be EC of x. Now we differentiate this equation so that dn of x by dx is equal to NC, it's a constant. E raised to EF minus EC of x by KT is to be differentiated with respect to x. As you know, E raised to AX, if we derive that, it is A into E raised to AX again after derivation. So here we have minus 1 by KT. Since EC is dependent on x, the derivative of EC, d of EC of x by dx into E raised to EF minus EC of x by KT. Now we know NC E raised to EF minus EC of x by KT is n of x. So I am just substituting back. So we get dn of x by dx is equal to n of x into minus 1 by KT d EC of x by dx. This value of dn of x by dx is substituted in the equation of the diffusion current. You can see what happens if we substitute the values. We get q dn n of x minus 1 by KT dEC of x by dx. So this change we have made in case of the diffusion current. Similarly, for the drift current, we know the slope of the conduction band gives the field, or the field which creates the drift current. If we want to mathematically represent the field, it is the slope of the conduction band in this case, since there is no external electric field applied. In order to find the slope of a curve, we need to just differentiate. So the conduction band EC of x is differentiated with respect to x and divided by the q, the charge. So we get the field, which is given by 1 by q dEC of x by dx. This we are substituting in the equation for the drift current. Minus q mu n of x fx was the term we had while we equated drift current is equal to diffusion current earlier. So that by substituting the value for fx, or the field, we get minus q mu n of x 1 by q dEC of x by dx. Now we simplify after substituting these values. At equilibrium, as you know, the drift current is equal to diffusion current, which is shown by the first equation. Now in place of dn of x by dx, we are substituting the value that we have obtained 2 slides back, and in case of fx, which is the field, we are substituting the value that we have got in the previous slide. So that at equilibrium the equation becomes q dn n of x minus 1 by kt dEC of x by dx is equal to minus q mu nx 1 by q dEC of x by dx. Now we can cut similar terms in both left hand side and the right hand side. There are q in both sides, it will be cancelled off. Then you are having n of x in both sides, that will be also cancelled off. And at last we have dEc of x by dx in both sides, that also can be cut off. The remaining terms we can equate. dn into 1 by kt is equal to mu into 1 by q. By rearranging this, we get the Einstein relation, which is given in the box. dn, which is the diffusion coefficient, divided by mu, which is the mobility, in this case mobility of the electron, mu n, which is equal to kt by q. As I had said earlier, we are finding the relation in terms of the electrons, and which can be mapped for holes too. So electrons, the diffusion coefficient dn is equal to kt by q, mobility of electrons. In case of holes, dp, which is the diffusion coefficient of holes, which is equal to kt by q mu p, which is the mobility of holes. As a summary, the Einstein relation states that the diffusion coefficient is proportional to the mobility of carriers. This is the Einstein relation. So we started with equating the drift current and diffusion current, because at equilibrium, when there is no external electric field applied, these two currents will be equal and opposite. And in that equation, we had substituted certain terms with the knowledge that we already had. The number of electrons, the electric field due to the slope of the conduction band. These were the concepts that we used, and at last we simplified it into a relation where the diffusion coefficient is related to the mobility of carriers. This is the Einstein relation. Next equation of our interest is the continuity equation. This comes from the fact that while we were discussing about diffusion of excess carriers, we were neglecting the effects of recombination. In few classes back, we had introduced the term recombination. Recombination is the process where the carriers fall into, maybe the electrons fall into the holes and it recombine, and so because of that the number of carriers reduces. It is the opposite of generation. Recombination is the opposite of generation. This recombination is also happening while the carriers are diffusing, but we were not considering that, we were neglecting it. But we cannot simply neglect the effect of recombination. We have to consider that too, because that causes variation in the carrier distribution. And if there is a variation in the carrier distribution, there will be a variation in the current in the semiconductor. In the explanation, we consider the hole current for a change. Until now we were just discussing about electrons and then mapping to holes. Now here we will think of hole current and then we will map to the electron. Imagine while the hole is moving from Jp of x, from a point x, it is entering into an area, where there is a possibility of recombination. The current entering that shaded area may not be the same, can be more or less while it leaves from the area, that gray area, or while it moves ahead of x plus delta x. Suppose we consider it as there will be an increase in all concentration. We are just taking it. Need not be increase in all concentration always. There can be a reduction based upon the material. The net increase in Hall concentration per unit time, which is given by dou P by dou T, will be the difference between the Hall flux per unit volume entering and leaving, because within that volume recombination is happening. This minus the recombination rate will give the net increase in Hall concentration per unit time. If we represent that thing in a mathematical expression, we'll get rate of Hall buildup dou P by dou T while the current or the Hall is moving from x to x plus delta x will be equal to increase of Hall concentration in the delta x area per unit time, which is given by 1 by q jp of x minus jp of x plus delta x by delta x, minus the recombination rate, which is given by delta p by tau p. Now, as delta x approaches 0, or the area, the volume that we consider is very small. Now we say that the area, the volume starts from x and extends till delta x. If the delta x is almost 0, then we can rewrite the current change in the derivation form as dou p of x and t. It's depending on the distance x and also the time t. That is why the partial differentiation is being used. You might remember studying the partial differentiation. We use that when a particular quantity is depending on more than one variable. Here the variable is the distance x and time t. That can be written as dou of delta p by dou t. We make necessary rearrangements in the previous equation. I will show the previous equation once again. We are taking that delta x is approaching 0. That is why we can rewrite the equation in this format. Dou by dou t of delta p is equal to minus 1 by q dou j p of x by dou x. Why we use dou instead of d? It was differentiation d. Why we are using dou, the partial differential? Because it is depending on two variables, more than one variable, and we are concentrating on one variable. We are finding the difference with respect to dou x minus delta p by tau p. This is the continuity equation for holes, and as we are doing, we are mapping it to the continuity equation for electrons. Only difference is that wherever there is a p, you are substituting it with n, and also the negative sign is lost because you know the sign of the charge of electrons is negative, so that negative and negative gets cancelled. So we have dou by dou t of n x of t is equal to 1 by q dou Jn of x by dou x minus delta n by tau n. This is the continuity equation, and it is having a relevance in our discussion about the current in a semiconductor. Though we had discussed about diffusion in our previous lecture, we were not able to write an equation which is called as diffusion equation. Though we had written Jn of bracket in diffusion, we were also considering the drift current. Now, when the current carried is strictly by diffusion, we are neglecting the drift. Then Jn of diffusion, which is equal to q dn dou by dou x of delta n. This dou by dou t of delta n is equal to dn from the previous slide, which I will show it once again. We know dou by dou t of delta p is equal to the term, or dou by dou t of delta n is equal to the term that we are substituting here, and we get substituting the dn terms into that jn terms in the previous equation. We get dou by dou t of delta n is equal to dn dou square delta n by dou x square minus delta n by tau n. Similarly, the diffusion equation for holes by substituting the n with p. What we have done is, in this equation, in place of j n of x, we are substituting now. Another important terminology or a concept is the diffusion length. Mostly in a steady state distribution of excess carriers, the time derivative is considered as 0. So in this equation, in the previous slide, in this equation, the dou by dou t term, which is the left hand side, can be taken as 0. So this equation can be rewritten as dn dou square dou n by dou x square minus delta n by tau n is equal to 0. And we rearrange it and we get dou square delta n by dou x square is equal to delta n by dn tau n, where root of dn tau n, dn is the diffusion coefficient and tau is the lifetime, the collision, the time, mean time between collision, or the movement of an electron or the carrier before it collides. So this term is known as the diffusion length. Root of dn tau n is known as the electron diffusion length, which is normally represented as L suffix n. And as we do, this can be mapped to holes. So root of dp by tau p will be the whole diffusion length LP. So with that, we will stop our discussion for the day. In our forthcoming sessions, we will be seeing few more equations related to, or a few more mathematical representation related to the semiconductors. What we have done in this video is that we have mathematically represented few concepts that we have already learned regarding the semiconductor. So we will see current flow equation, gradient of quasi Fermi levels, Poisson equation, and there will be a tutorial on this session, and we will be moving on to the PN junction in the next module. So thank you.